Okay, hello everyone. I think we're live with this webinar. Welcome to our LiDAR QC Tools webinar today with the title Unveiling the Power of LiDAR SLAM for Point Cloud and Trajectory Adjustment. Thank you for joining our webinar. It seems like we have a big audience today and we really appreciate your interest and your participation. I'm happy to host this session today. My name is Nico Jäger. And I'm the product manager of POSPEC, which is our post-processing software for GNSS inertial data. I'm joined by Anna, who is our product manager for our land products. Anna will help today to answer questions during the Q&A session. And in addition, we have also Santia here from our marketing team in case we have any technical issues, which I hope will not be the case. So before we start, I wanted to raise your attention to our previous recorded webinars, which you can watch in our webinar center at applanix.com/webinar.htm at any time you want. Okay, some words about the logistics. The presentation will last approximately 30 minutes. And then we'll have time for 10 to 15 minutes for the Q&A session. The webinar will be recorded and shared with you after the session here. All attendees are muted. And in case you guys have any questions, please enter them into the Q&A box at the bottom. And we will try to answer them after the presentation. Should we not have sufficient time to answer all questions during the presentation or webinar here, we'll get back to you in an email and definitely provide an answer to your question. Okay, so what's on our agenda today is we'll have a look at what LiDAR QC is and how it works. We'll speak about the features and the deliveries that comes out of LiDAR QC. Sure, if you have a certain module you want to process data, you have some requirements. So we'll look into this one. Boresight patterns, what are the ideal Boresight patterns when it comes to Boresight calibration happening in LiDAR QC. We'll look at that one. I have some examples and some nice pictures so you can see what LiDAR QC does with the point cloud. And then we focus on a performance study, so you can also get an understanding of, what the accuracy is, what we can get out of this. Then summarize the benefits and speak about the summary in general, and then we get to the Q&A session. Okay, so what is LiDAR QC? The Applanix LiDAR QC tools comprise a set of POSPEC software tools. Basically designed to attain the utmost level of georeferencing accuracy with LiDAR sensors. So primarily employed in the uncrewed airborne sector, in the land mobile mapping sector, and in the indoor survey industry. This software is basically hardware agnostic, functioning seamlessly with any LiDAR system. Ground control points or ground reference data, again, such as ground control points, they are not necessary. The primary objective here is to generate a consistent and homogeneous point cloud by refining the vehicle trajectory using the LiDAR data. So LiDAR QC creates really dramatic improvements, particularly in GNSS critical environments, where the system is subject to drift effects. And the technology that we use here is called Applanix Point Cloud Data Adjustment, in short, PCDA. So as I said, the Applanix Point Cloud Data Adjustment technology that we use here represents an advanced iteration of LiDAR simultaneous location and mapping, in short, SLAM. I trust you guys have heard about SLAM before. And this one is founded on a robust global voxel iterative least squares adjustment. And in this context, the LiDAR serves as an aiding sensor contributing to trajectory optimization, basically. So this optimization is generated in passback utilizing the data collected from the Trimble inertial hardware, such as the Trimble Applanix POS systems or the AP Plus or AP systems that you guys are aware of. So features and deliveries from LiDAR QC. So the trajectory adjustment using the PCBA technology compensates for errors such as the GNS inertial trajectory inaccuracies, Boresight angles, any sensor errors, and of course also data acquisition errors. And the final goal is to generate a homogeneous matching point cloud. Here on the right side, you can see an example of data acquired in Toronto, downtown in Canada. So on the left side, you can see the street lamp that was basically collected from different sites at different times in a very critical GNSS environment. And that is the result of the point cloud before you run LiDAR QC. Well, after you run LiDAR QC and you improve the trajectory, obviously the point cloud is supposed to match. And that's what you can see here on the right side with that street lamp. So what are the deliveries? I mentioned already the corrected trajectory, which is, I think, the key function of LiDAR QC. This is going to be the SLAM adjusted aspect file, if you want to say, that is the one that we use for the point cloud georeferencing. And beside the corrected trajectory, LiDAR QC can also estimate the so-called Boresight angles. And Boresight angles are a constant misalignment between the inertial sensor and the LiDAR sensor. You don't want to measure, obviously, the angles for the vehicle or for the inertial system. You want to measure everything related to the sensor, which in this case is the LiDAR sensor. So LiDAR QC can estimate the Boresight angles. And eventually, if wanted, you can also create the point cloud directly in POSPEC, and it can generate hence the known LAS file for the point cloud. So that SLAM adjusted trajectory that you can create in LiDAR QC can obviously be used also for direct georeferencing of other sensor data, not just the LiDAR. The LiDAR is like an aiding sensor here that helps us to get a better trajectory out of the standard GNS inertial processing. But if you have this good trajectory, you can use that for direct georeferencing of other sensor data, such as a camera, a radar, or hyperspectral sensors, or whatever sensors you use for direct georeferencing. Another nice feature of LiDAR QC is that we support a so-called selective adjustment. In this context, we'll focus on critical trajectory segments. You can imagine that if you drive in, let's say, 8 hours of data and only 2 hours of the data are critical because you were or the vehicle was subject to significant drift effects in a very critical GNSS environment, you probably don't want to run LiDAR QC over 8 hours of data, but just focus on the 2 hours where your solution is not perfect, right? So in LiDAR QC, you can assign a certain RMS threshold, let's say 10 centimeter, and LiDAR QC will then only adjust those segments that are critical where the RMS is over 10 centimeter, for instance. That idea will accelerate the entire LiDAR QC process. So LiDAR QC process does finish a little earlier, obviously, and it will still create one single homogeneous adjusted aspect file. So here's the workflow given in a diagram. What do we need for LiDAR QC is ideally the aspect file, which is the smooth path estimate of trajectory. You can also input an RTK corrected trajectory or an RTX corrected trajectory, and then load your raw LiDAR data into LiDAR QC. And then you can make a decision, do you want to have the Boresight calibration or do you want to have the adjustment? In both cases, whatever you decide for, at the end, you will export your aspect file in your target mapping frame, for instance, the NAT 83 in America or the ETRS 89 in Europe. And you apply the adjusted aspect file and of course the Boresight angles that you calibrated. And then you can continue in a third-party software to create your point cloud, or you proceed within POSPAC, you export your aspect file at your custom target frame. At this time, you don't apply the Boresight angles. And then in our last creator software, which is part of the LiDAR QC, you would just take this custom aspect and create the point cloud inside of POSPAC. So these are basically the workflows that you can apply here. So LiDAR QC is also batch command line and POSPAC cloud compatible. So the batch command line executable triggers automated processing without running POSPAC in the graphical user interface. That means users can define a batch template, which is an XML file, to be used in a production environment where only basically the input parameters or the raw data really change between the different missions, which is the rover data and if you have the base station data. But the batch command line processing itself triggers like a single execution function that does increase the productivity, efficiency, and it does reduce also the user operational mistakes, such as someone enters wrong lever arms or wrong rotation angles. That can happen, and you would get not good solutions. Well, when you use the batch mode and you have a template, you will reduce those mistakes. Integrators can use the batch command line to implement it into their own piece of software. So that means POSPAC graphical user interface does not need to be launched or used at all. Creating a batch file is also a prerequisite for our POSPAC cloud onboarding. And LiDAR QC is fully supported in the POSPAC cloud environment, and it relieves users really of purchasing high-end fast computers. You can imagine with LiDAR QC where you have a lot of point clouds, you need to have a good computer, a fast computer. There's some requirements for that. When it comes to going into the cloud environment, it is the vendor who is responsible to provide the proper IT infrastructure. And yeah, POSPAC Cloud does that, and POSPAC Cloud services also monitored 365 days a year, 7 days a week, 24 hours, and it's supported by a redundant infrastructure. Here on the right side, for instance, as an example, we have a status page where customers can subscribe to, and then they would see the status of the cloud environment, for instance, for planned outages or unplanned outages, etc. The uptime is visible for customers, etc. Okay, that brings me to LiDAR QC requirements. So first of all, of course, you would need to have the raw LiDAR data, and those data need to be available in the native LiDAR frame, time tagged with the GNSS INS data from the Trimble Applanix hardware. That's quite important. In addition to this one, you would need to have a LiDAR QC license, which is a term license for POSPEC. That term license typically runs over 12 months, but customers can also decide to purchase multi-years upfront, up to 5 years. The longer you purchase that term license upfront, the more discount is applied. So post-processed aspect file needs to be available, as I said before in this workflow diagram. Or if you have an RTK or RTX corrected real-time trajectory, that also suffers the purpose here. Precise lever arm, which is basically the offset between your reference point to from the reference point to the LiDAR sensor. That is important. Typically comes from the integration from a CAD model, but that needs to be very precise, of course. And you would need to have some pre-knowledge about the rotation between the IMU and the LiDAR frame, which is also known as the Boresight calibration. LiDAR files itself are available as following formats. So we have our own internal format, or let's say we have two. One is called the generic 5-double format, but we have also an advanced float format, which we call LQC format. So users to integrate a LiDAR would typically need to convert the native format into one of these formats to make it readable by LiDAR QC. But in addition to this one, we have some other formats that we support directly already, which is the PCAP Velodyne format for the VLP16, VLP32, plus the format from the Hesai Panda XT16 and 32. And of course, we also support the Trimble MX TMAX native format. For Boresight calibration purposes, we clearly have instructions on how the Boresight pattern needs to look like to make sure that the Boresight calibration does converge properly and provides you reliable values. And as I said before, a state-of-the-art computer with large RAM. So large memory is absolutely needed to process many of those, millions of those points in LiDAR QC. So here are the formats that we support. I said the 5-double format, and the minimum information really is the time information, and then X, Y, and Z distance from the LiDAR in their own native frame, and intensity information. The LQC format is the second one that we support. It has just a couple of more fields, such as classification or return and scan information. We do have good documentation about those formats for users who need to write a converter. Let's get to the Boresight pattern. First of all, the suggested Boresight pattern for mobile mapping application. What we suggest here is 2 perpendicular strips with opposing runs. So each strip has consists of 2 runs in opposing directions. And those strips are perpendicular, so like at an angle of 90 degrees, for instance, which you will get from the standard environment. What we also suggest is there is some structured scenes on the ground, like you can see here, residential area with detached houses. So those houses are not very high. We're not suspecting bad visibility to the satellites. So of course, open sky terrain makes kind of sense here, which means you shouldn't be going really in downtown area where you have tall buildings and skyscrapers and that kind of stuff. The strip length does not need to be longer than 300 meters. Of course, you can always add another strip if you want to increase the redundancy, specifically for low-grade GNSS INS systems, for instance. And the Boresight pattern for the uncrewed airborne industry looks quite similar. which are just like 4 parallel strips, also flown in opposite directions, and a few perpendicular strips forming multiple crosses. Basically, the terrain needs to have some distinctive ground features, specifically at the cross sections, to allow LiDAR QC to converge properly. And yeah, we shouldn't be creating any gaps on the ground, so a decent side lab of 50% makes sense for a perfect calibration pattern. So now let me get some examples to you. So first of all, here from a mobile mapping application, on the right side, you can see the mapped area. Here, it was really in an urban environment. And on the left side, you can see a plot that shows us the difference of the original aspect. So the original aspect derived from the GNSS INS processing versus the LiDAR corrected aspect. And you can see the differences in northeast in the down component. The maximum peak for the down component was close to 40 centimeter here, and the maximum peak for the horizontal component about 25 to 30 centimeter. So this is how much LiDAR QC corrected the trajectory because the system was really exposed to drift effects and difficult GNSS tracking. And the flat lines at the beginning and at the end are obviously the time epochs where we didn't have any LiDAR data. So you can see that the aspect file gets obviously only corrected for the parts where, or for the segments where LiDAR data are present. Here's an example of so-called vertical mismatch. So imagine you collect data from one road, and at some point you drive the road in the opposite direction, or you have a cross section so you can see the scene twice. So you basically have revisits, and if you draw a cross section through this revisits, you may see point clouds that don't match exactly to each other. And in this specific example, we have a difference of close to 9 centimeter. And the job of LiDAR QC is to remove this conflict of the 9 centimeter and match the point cloud from all the individual runs and the revisits of the same scene. Same example is given here just as a horizontal mismatch. You can see the road paintings for a parking lot here on the left side before LiDAR QC. Basically, you can see this doubled, and there was a horizontal mismatch of about 30 centimeters, and LiDAR QC will remove that conflict. On the right side, you can see the situation after LiDAR QC. So while the LiDAR QC tools process does not encompass ground control points, it effectively improves point cloud accuracy over these ground control points. We've seen that a couple of times. This enhancement is attributed to the compensation for drift and noise inherent in the LiDAR SLAM technique. So on the left side, again, before LiDAR QC, you can see that the point is not right at the strip painting corner on the road, and after LiDAR QC, it gets far closer to the reality. And I have another example here. The expectation of the ground control point is in that blue square at the lower right corner. And before LiDAR QC, you can see there is an offset here, a couple of centimeters. And after LiDAR QC, it is just right on top, and it does match with the expected position. Here's an example of an uncrewed airborne mission. Same as before. On the left is before LiDAR QC, on the right is after. So you will notice that the image on the left side is far noisier than on the right side, which has really straight lines. And then there's a cross section here through the building from different directions. So on the left side, you can see that the roof, the representation of the roof is far noisier, and that's also the walls. If you look at the verticals, and on the right side, this is matching up. You have straight lines and you have a clear understanding of what the roof pattern is. Also, if you look at the intensity image, colorized intensity image, on the right side, you can see that there are vehicles, basically, which you couldn't detect on the left side. That could have been bushes or trees or whatever. So you can see how sharp the situation becomes after LiDAR QC. And here's another example for the uncrewed airborne segment. Same thing, a cross section through the building that you can see there on the left side. Kind of noisy data, especially on the roof. If you look on the right side now, you can see the clear structure of the roof after LiDAR QC, in addition to the straight lines of the wall. Okay, let me get to a performance study and give you some numbers. So the primary objective of this exercise is to showcase the absolute accuracy in the 3D point cloud, both before and after LiDAR QC. The data collection took place in a town center through 2 runs in the same direction, in this case, forming loops with overlapping point cloud scenes. Each individual run or loop covers an approximate distance of 1 kilometer. And the town center proves really challenging for GNSS due to the narrow roads that measure only 4 to 8 meters in width, and the buildings reaching heights up to 12 meters. And you can imagine this creates really canyon. And the vehicle drove through this canyon for approximately 10 minutes with really poor satellite visibility. So in terms of the ground control points that you can see here, both 3D and vertical points were distributed over the entire area. And these points were surveyed through the establishments of a dense reference point network using GNSS technology and a Trimble terrestrial 3D laser. So basically, the entire area was scanned in a static mode before to lay out all of those ground control points. All of those surveyed points are referenced in the European Terrestrial Reference System 89, in short ETRS 89 frame. And to mitigate any potential datum defects, the same base station with the same coordinates, obviously, was utilized for the ground control point survey, as well as for the GNSS INS trajectory post-processing, which we did in a single base mode. This is the best approach to avoid any potential datum shifts. So the critical canyon segment with poor satellite tracking is what you can see here. That one really shows you the number of satellites that we tracked during this session. And in the red frame or the red rectangle, you can see the critical canyon part. So the GNSS INS trajectory, also known as the SBET, smooth best estimate of trajectory, underwent a post-processing in the latest Ion Fusion Plus single base mode. That supports all of the signals, by the way, and the frequencies right now, but with a maximum baseline of 3.5 kilometers. So within this challenging town center, characterized by the narrow roads, as I said before, and surrounded by the buildings, the majority of the GNSS epochs were in so-called float mode due to the satellite shading and not in the fixed mode. And the highest, or let's say the worst, estimated 3D root mean square RMS value in the GNSS-INS Kalman filter process was approximately even 50 centimeters, so half a meter, and not better. Okay. So the system that we utilized for that performance study was the MX50, the Trimble MX50, which is equipped with 2 LiDAR sensors, left and right, and a spherical camera, and an AP20 GNSS-INS system from Applanix, from Trimble Applanix. So here we have the final accuracy, which is separated by vertical and horizontal performance. So let's have a look at what the results were before LiDAR QC, which is here in the vertical component. The min and max error here was about close to minus to plus 9 centimeters, resulting in an RMS of 3.8, close to 4 centimeters. After LiDAR QC, we have a minimum error of minus 3 centimeters, close to minus 3, and plus 3 centimeters. So we came down from 9 to 3 at the maximum minimum error, and the RMS improved to 1.4 centimeters. We used altogether 24 vertical ground control points over the 1 kilometer trajectory. For the horizontal component, we used 13 points, and before the LiDAR QC adjustment, our min error was about 4 millimeters, and the maximum was even 17 centimeters, resulting in an RMS of 8.4 centimeters. After LiDAR QC, the max error came down to close to 5 centimeters, and resulting in an RMS value of 3 centimeters. I have to say that the horizontal points were not some, like targets. They're really road paintings, and sometimes it's not that easy to pick them, which probably adds a little bit to the horizontal results here. But overall, what we are seeing is a significant improvement. That means the 3D accuracy has been enhanced from 9.2 centimeters down to 3.3 centimeters, indicating a 280% improvement through the use of prospect LiDAR QC tools. So let's get to the LiDAR QC benefits. As I said before, LiDAR QC does not need any ground control points right now. It does a good job without it. We support a partial adjustment. So LiDAR QC can focus on very critical themes. It does not need to run over all of the data that you collect. The trajectory optimization benefits mostly, obviously, in weak or denied GNSS locations. If you're in open sky, in perfect environment, the impact is obviously not as big as if you are exposed or subject to your system subject basically to GNSS outages. LiDAR QC is supported in our cloud environment. It works with any LiDAR, in a sense, hardware agnostic. Beside the trajectory adjustment, it can estimate Boresight angles and run the Boresight calibration, and it can also create LAS files, so the point cloud at the end. And of course, you can imagine specifically with low accurate GNSS-INS systems, LiDAR QC can be very helpful to still get a very precise georeferencing information. And eventually, LiDAR QC shall ensure that we have a homogeneous point cloud. That's the main target. And the whole thing is, very good automated. There's not many parameters that this module needs. It's it's basically a one-click function, and it will do the job for you. Okay, let me get to the summary. LiDAR QC tools utilize LiDAR data to optimize the GNSS INS trajectory, functioning like a SLAM to ensure consistent point clouds for precise 3D mapping. So whether you use a low-grade surface scanner, so 360-degree scanner, or a precise mapping scanner for LiDAR SLAM, doesn't really matter. You actually add more observations to the GNSS INS trajectory processing, which improves the trajectory quality and eventually the 3D point cloud for the mapping purposes. Okay, so that brings me to our Q&A session, and I now rely on the help from Anna. Anna, do you have any questions in the chat?
Yes, I do.
Answer?
Yep. Thank you. Thanks, Nico, for the great descriptions and also all those results you've shared. Yeah, so I can see there's definite interest with some good questions coming through. I have some both in the chat and then a few in the QA as well. So yeah, we'll just start with the first one. Does LiDAR QC use the intensity for correction?
No, we're not using the intensity. Basically, what LiDAR QC does is it creates so-called voxels in kind of revisits, so in scenes that the LiDAR from the left and right side, or because of really physical revisits, can see twice. So we create kind of voxels, which is similar to pixels in the image world, and similar to when you run, for instance, error triangulation in the image world. So what we do is we create those voxels and look for identical planes, and then correct the aspect file during the least squares adjustment.
Perfect, great, thank you. Moving to the next one, this is another good one here. Is it possible to use with USV plus LiDAR, i.e. in the sea or river?
Say again, so someone wants to fly over a river and improve the data, or did I get that right?
I was reading it more like let's say not a UAV, but you know, a drone on the water, if they're going along the rivers under, I guess, little overpasses and such. So can it run on a boat is how I read that.
I think as long as you have yeah, it should definitely work. Of course, the data, any data that go undersea shouldn't really work, I guess. But everything oversea, that as long as you have buildings and planes that you can see at least twice, it can be used to correct your trajectory also on a vessel, and hence improve the point cloud at the end. Yeah, I have no doubts that should be working.
Perfect. And another one here for Trimble MX9. So does it work with Trimble and MX9 mobile mapping systems?
The same concept like the MX50 that's out there. So yes, it works.
Yeah, perfect. Oh, here's another good one. Okay, so someone's interested in processing previous aerial survey data. So can they reprocess that now using the QC tools?
Yeah, of course, that's not a problem. Again, what we need is just the aspect file, the trajectory. It doesn't matter how old that is. And as long as you have time tagged raw LiDAR data, that can be used, no problem.
Perfect, great. Another one here, sort of on the algorithms of the matching. So how is LiDAR QC working when matching the different runs? Just using one as a reference to match to the others, or something more sophisticated?
No, it's not like a strip adjustment where you go strip by strip sometimes. This is an overall least squares adjustment. As I said before, it works similar like an error triangulation. So it creates those voxels overall of how many runs you have, and it detects identical planes basically, and it throws everything into one single adjustment, and it comes up with the improved trajectory. So it's not like one is a reference and it will correct one to the other all the time. Similar like a strip adjustment. It works differently.
Perfect, thank you. Another good one here. Will LiDAR QC work within Trimble Business Center?
That's something for potentially the future. I don't know. Right now it works in Prospect, and what the future brings, so we'll see.
Right, makes sense. Yep. A few more. Still quite a few coming in. I'll try and pick a couple more here. So in your example, the environment is quite feature rich. How does it work in feature poor or repetitive environments?
Yeah, I think we don't have that many reference data right now in an environment where you don't have really a lot of features. I mean, we know that it works we've seen it working even in tunnels. That's great, but I can imagine if you go on a highway in a desert, that might create some issues. But we don't have reference data to really comment on that one. Again, in tunnels, we have seen it working.
Perfect. Yeah, that was actually another question. So does LiDAR QC work in tunnels? So we've replied to that one. Okay. Just trying to scroll down. There's quite a few here. Maybe we'll take a couple more and then we might have to follow up after. So let's go with this one here. So questions, I guess, on GCP, these always come up. I think you addressed it, that we can use them to check, but basically the question is, you mentioned no GCP is needed. Does it support the use of GCP when available?
No, as I said, so LiDAR QC right now does ignore GCP. So we cannot feed any ground control points into this process. If you have any ground control points, you can use them later to bring the point cloud right over those ground control points, while LiDAR QC makes sure that all the data are matching perfectly and you have the perfect trajectory, which hopefully means that you have a good match with your ground control points already. But then if there is still an offset, for instance, a datum shift or something, this is a separate process right now.
Perfect. And I'll just go with one last one. Maybe it also help answer some of these lingering questions. So someone's asking, can I have a demo license?
Of course, everyone can have a demo license. We're happy if you guys test it out with your integrated system. So just send an email to techsupport@applanix.com, and we will be very happy to give you a demo license.
Excellent. Well, thanks so much, Nico. The questions are coming in faster than we can get to them, so probably we'll just have some offline conversations. But yeah, it looks like there's a lot of interest, shared a lot of good results. So yeah, I want to thank you and thank you everyone for their questions as well.
Yeah, thank you very much, Anna, and thank you very much everyone who attended. As Anna said, if there are any open questions, we will definitely get back to you. We are always anytime available for you guys. So you can send always an email to techsupport@applanix.com, but you can also touch base with Anna or myself anytime when it comes to LiDAR QC. So I really appreciate your participation today, and I hope to speak to you guys soon. And thank you very much for your attention. Take care. Bye-bye, everyone.